Welcome to Chapter 3, Unit 2, Quadratic Functions. Recognizing characteristics of parabolas. The graph of a quadratic function is a parabola. So if you are not necessarily familiar with the quadratic function, we did go over that previously, but let me remind you, it is anything that looks like this. This is probably one of the few functions you guys have worked with before. It is just a basic function. Our toolkit function would be x squared. That's also the parent function. So it is a parabola. So every quadratic will be a parabola. So it will be a parabola. It will either open this way, it'll open this way. Sometimes they'll open sideways. It is a parabola, but it's, it fails the vertical line test. So it's technically not like really a function, but we do still cover them. So the vertex, notice that is this point in this graph, that lowest lying point when it points up and the highest point when it points down. It's an extreme point. It's the point where it starts curving back on itself. So it starts making a bowl. The axis of symmetry, notice that red line, this guy, runs right through the vertex. It is where you would be able to fold the graph in half and it would be symmetric on both sides. So like, for example, if you were in art class, if you drew one half of the graph on a piece of paper with paint and then you folded it over, the paint would smush together and you would have the exact copy of the other side. So it is completely symmetric. That's an important point to remember. The x-intercepts are what we will call roots or zeros, and I'm just going to make sure I've covered that. Here, x-intercepts are called roots or zeros. They're the point where y equals 0. So when you are told to solve for x, you are finding a root. So, solve this for x where y equals 0. So like what we did in the previous problem. So simply setting this equal to 0, you would solve for x. Those are the roots. So we need to also understand how the graphs of parabolas are related to their quadratic functions. So notice the general form of a quadratic function. That is the general form. They have to be real numbers, a, b, and c, and a absolutely cannot equal 0. If a equals 0, you get just a linear function. Notice that if a disappears, you get bx plus c. So that's not going to work. If a is greater than 0, the parabola opens upward, which means it'll look like this. If a is less than 0, the parabola opens downward, like this. And once again, if a is 0, it's not even a quadratic function because it just turns into bx plus c. The axis of symmetry, that's this guy. This is where x equals negative b over 2a. So you would use these guys to find it if it were in general form. And I'll highlight that because you guys will probably use that. Now the standard form, or as you'll often hear it, vertex form of a quadratic function, that's this guy right here. So notice that hk is the vertex. H is negative on the inside, so it's going to be the opposite of whatever sign you see. So if we got x plus 4, our h would be negative 4. If we got x minus 4, our h would be positive 4. This is the most useful form when we want to figure out how it was transformed. So right now I'm going to do some Desmos. And we will do f of x. It's going to be equal to ax. Where's my caret? Ax squared plus bx plus c. I'm going to create sliders for all of them. So I am going to take my c all the way to 0, and I'm going to take my b all the way to 0, because this is the parent function, the toolkit function. Notice the axis of symmetry is just the y-axis because the vertex is 0, 0. So here we would have f of x equals x squared. And if our axis of symmetry is negative b over 2a, a is 1, b is 0. So it's going to be our axis of symmetry equals 0, x equals 0, and that is the y-axis. So notice as I start making a larger, I start smushing it closer to that y-axis. As I make it negative, notice that it flips over. So here, this is the parabola opens upward, and here the parabola opens downward. Upward, downward, upward, downward. And that's all because of the sign on A. Notice that as I take it to the more extreme of the negatives, it smushes closer to the negative y-axis, which is exactly what it does when you take it to the extremes with a positive. The graph gets quite large as it becomes a fraction, as a becomes a fraction. Notice that. So let's put our a back at 1. Ooh, there we go. Now we're going to mess with our b. We're going to see what b does. Looks like b does some type of transformation. So what can we get from b? Well, when b is 0, it's just your normal f of x equals x squared. As we make it more towards a large positive b, notice that our vertex swings into the negative region. So it's a negative x and a negative y is where our vertex becomes. Now if I were to swing this b to be negative, then my x vertex would be positive because it swings into that positive x, negative y coordinate. So it looks like b is going to mess with the value of our x coordinate for our vertex, and it's going to also mess with the value of our axis of symmetry. Notice that when b is negative, our axis of symmetry is positive. When b is positive, the axis of symmetry is negative. So we'll set that back at 0 and see how just the c affects our graph. Looks like the c just moves it up and down, as you would expect. So how about, let's make a wide, super wide one. There we go. That's negative 0.1, so it's negative. See how b affects that? It's like it swings the vertex along its own path of a parabola. So each single one of these will affect it differently. So that's this form. Now let's have a look at the form we were talking about. So we're going to do a x minus h plus k. So I'm going to get rid of b and c because I no longer need them. Let me make this squared. There we go. Okay, I'm going to set a back at 1. I'm going to put k at 0 because remember hk is our vertex. I now want my vertex at 0, just like I had for my original ax squared plus bx plus c. We're going to see how this affects it. So as I make my h positive, it's going to move to the right. As I make my h negative, it's going to move to the left. And this is because h is the x coordinate of our vertex. Now what about the k component? The k component is on the outside. So it is going to move our stuff up and down. So the larger k is, the more it goes up. The less k is, the more it goes down. And A is still responsible for stretching it and compressing it really close. So that's what we are looking at. So this is how the graph is transformed from the toolkit function f of x. I would recommend going on Desmos and just playing around with it, seeing if, you can maybe kind of guess where it goes. Again, notice that the x coordinate of our vertex is that axis of symmetry, which is also the h. And if you wanted to find the y component, you would find k, which is f of h. So the domain and range of quadratic functions. The domain of a quadratic function, that's all the x values that can go in, is every single one of them. All real numbers can be put into a quadratic function. And also we learned previously that complex numbers can also be put into quadratic functions. So the range of a quadratic function are the y values. So notice if we were to graph something. When we have a negative, we'll get this. Now our domain here, our range here of x values are all the x values that are less than our vertex. But when a is greater than 0, when it opens upward, our y values are all the y values that are greater than the vertex. These are examples of when something might have a complex solution. I'm just going to let you guys know that based off of graphs. If it does not look like it physically intercepts the x-axis, it is more than likely it's going to have a complex solution. If that makes sense, because obviously it's not intersecting at a real number, or else it would be intersecting somewhere along here. So the easiest way to determine the domain and range of a function is from its graph. And that's okay. You can graph a function here. That's totally fine. And you can determine domain and range that way because graphically is acceptable. Determining the maximum and minimum values of quadratic functions. So as you could have guessed, the maximum value of a quadratic function occurs when a is less than 0. The minimum value occurs when a is greater than 0. Notice when a is greater than 0, you will have no maximum. And notice that when a is less than 0, you will have no minimum. So let's see if we can look at some examples. So for the following exercises, we're going to write the quadratic function in standard form, and then we're going to give the vertex and axes intercepts, and then we are going to finally graph the function. So we will do number 7. Okay, so we have to write this in standard form. Remember, standard form is plus k. And we are given x squared minus 4x minus 5. So the first thing we're going to do is we need to complete the square. Now when we complete the square, and if anyone needs to look this up, I know there's tons of videos on YouTube. I'm usually pretty rusty at doing it. It's not something you do beyond really probably your second college level math class. Yeah, it's not like a super standard thing. If you go into calculus, you will encounter this rarely. So if you are rusty, that's fine. Just look it up. It's okay. So complete the square. The first thing we're going to do is we're going to move everything over that does not have an x. So that is plus 5. Now we're going to take this negative 4 and we're going to cut it in half. So it becomes negative 2. And then we are going to square that. So it becomes 4. And we are going to add that to both sides. And then we are going to factor this right here. And just so you know, it will come out to x plus whatever is in here. That's usually what happens. So it's plus minus 2 squared. And that's going to equal 9 because we added these guys together. And that gives us minus 9, which is what we would get. So this means the vertex is 2, because remember it's the opposite sign of whatever is on H, and then the same sign of whatever is on K. The x-intercepts, that is where y equals 0. So let me scoot this over a little bit. So the x-intercept is where y equals 0. So that's going to be, this will be 0. X minus 2 squared minus 9. So it's 9 equals x minus 2 squared. And then take the square root of 9 and the square root of this, which is going to be x minus 2. And remember, we get plus and minus 3. So we have minus 3 equals x minus 2, and positive 3 equals x minus 2, which gives us x equals minus 1 and x equals 5. Now we can plug those back into the original to see if we do actually have the correct answer. So that's going to be minus 1 squared, which gives us 1 plus 4 minus 5, which is 5 minus 5, which is 0. So we're good there, which means I'm going to go ahead and assume that the 5 is accurate also. So this means that if I guess I'll go this way. So if I were to graph it, I know my vertex is at 2, 9. So we're going to go over 2. We're going to go down 9. So I'm going to say that's my vertex. And my x-intercepts are when x equals -1. No, I think that needs to be over more. Maybe right here. There we go. When x equals -1 and when x equals 5. So we'll say this is where they are. And we would just draw it. Sketch it like that. So now we need to find the quadratic equation using the given information. And I am going to go with 9. So we're going to solve that one. So for number 9, we know that f of x equals a, x minus h squared plus k. So if my vertex is -2, 3, I'm going to have a, x plus 2 squared plus 3. And a point on my graph is going to be 3, 6. So what that means is when I put 3 in for x, I'm going to get 6 for y. 3 plus 2 squared plus 3. And now I'm going to solve for a. So I have 6 minus 3. And that is going to give me 3 equals a, and then 3 plus 5 squared. So that's 3 equals a times 25. So a is going to be 3 divided by 25. Okay, and that gives us f of x equals 3 divided by 25. X plus 2 squared plus 3. And that is what that would look like. So now if we wanted to do, we have number 11. So a rectangular plot of land is to be enclosed by fencing. One side is along a river and needs no fence. So this needs no fence because this is a river and it doesn't make a whole lot of sense to have a fence there. So the total fencing available is 600 meters in total. So now I need to find the dimensions of the plot to have the maximum area. If the area of a rectangle is this, we'll call this the length, this is the width and the width. Notice we only need one length side. It's going to be length plus 2 times the width is equal to the total perimeter of the fencing we will need. So we only have 600 meters in total. So it wants us to maximize the area. Maximize the area. We want to maximize the area. So I'm going to go ahead. We know that the maximum amount of fence we can have is 600 meters, right? Okay. So I'm going to go ahead and solve for L because it will not involve fractions. Now I know my area in terms of L, and I'm choosing L because it's what I solved for. is going to be length times width, which is 600 minus 2w times w, which gives us 600w minus 2w squared. I'm going to rearrange. Plus 600w. Now we need to find the w coordinate so that we can plug that back in to this so that we can find the amount of fencing in the area. So one thing to make note of if you didn't want to complete the square here, notice that you don't have any extra numbers added on, so we can actually do this. You can find the roots, and then you can find the x in between them, or you can use x equals negative b over 2a, and this you could use even if there is a c. That's usually attached to the end. So let's see what that says. Negative b is 600 divided by 2 times a is 2. It's negative 600 divided by 4. And that will be this is negative 2. And that will be positive 150. So if our, and of course this is w, right? So if our w equals 150, then our length equals 600 minus 2 times 150, which is 300. So we're looking at something like this. But the river is on this side. That area is going to be 300 times 150, which is 45,000. And that's the area. Square meters. So that sums it up for 3.2 quadratic functions. And I will see you in the next one.